Okay, so as I told you in the RTDS, we design any power system network. So we use the software RSCAD. Okay, so let's say this is the 9-bus network. Okay, so we can design our own network also. Let's say Uttarakhand network or anything. So we can design this network. So from this, let's say a PMU is placed at this bus. Okay, so we can take the voltages, three-phase voltages, and let's say the current out of this bus. Okay, let's say those three voltages and three-phase currents we are taking out. So that we can do using the GTAO card. So let us consider a simple example now. So let us take this as simple example. We have just one source and one load, and we have actually this is one transmission line. Okay, so let's say this is just one transmission line. We have divided it into two parts to create fault at any X percentage of location. So now we are using this GTAO module. Okay, so the input of these three is, so here if we click, and so here we can, as I told you, we have 12 channels, so we can use at a time 12 channels. So we are using here 6 channels, so 6 channels we have enabled here, and the input to this is three-phase voltages of this bus. And if you click here, not this one, so here the three-phase currents, so this IA, IB, IC, and these three-phase voltages that we are giving as a input to this GTAO card. Okay, and this is the fault logic that we have developed. So for and it has this fault resistance and at which percent we are doing. So this we can develop in the RSCAD. So we have to just compile and we can run here. So we can run in one of the racks. So this is currently running right now, and after this there is some scaling conversion we have to do. So I have taken this example here. So let's say here the input is 230 volt, 230 kilovolt. So 230 kilovolt RMS. Then we have to find the peak value. So 230 kilovolt divided by root 3. So this is line to line voltage. So divided by root 3, we'll get the phase quantity, and into root 2, we'll get the peak value. So this is the value which we need to give as a scaling to the GTAO. Okay. So here if we, so here three phase voltage, the scaling, the 187.79, this is the peak value of the phase voltage. This we have given here. Then the output of the from RTDS, let's say we the plus minus 10 volt only we can get. So here we have just taken for safer side 5 volt only. So this 187.79 is interpreted as 5 volt out of the GTAO card. Okay, and from the GTAO card we are giving it to the amplifier. Amplifier is amplifying it into 300 volt, 300 volt for the voltage and maximum 32 ampere for the current. So this is the conversion. So 187.79 is converted to 5 volt, then 5 volt is converted to 300 volt. Okay, so this value 625.96, this we have to give as a scaling factor in the CTPT module of the PMU. Then only this 230 volt kilovolt will be, the same voltage will be shown in the PMU also. So this is the conversion that we have to give. I will show you where we have given this 625.96. The same thing is, let's say we will know the rated current at the particular transmission line. We will take, let's say 20-30 times. Let's say our current maximum can go 20-30 times. So we are taking, let's say 30 kilo ampere. The same thing, we will calculate the peak value. This 24.5, this we have given here. Uh, so 24.25 we have given here, and that 25 will be scaled to 5 volt, and then in the GTO card it will always considered as a voltage. We have to enter the current also is interpreted as a voltage, and that we have to convert. So maximum output of the from the amplifier is 32 ampere. So 24.5 30. So this is the scaling factor we have to give in the CTPT module of the PMU. So this is the conversion. So no, this at the PMU CTPT. So this at the amplifier we are getting 300 volt output. That 300 volt we have to interpret as 187.79 kV. So this 300 volt into this 625.96, if we multiply, we will get this value. So at the PMU we will know that we are getting 187.79. Okay. So from amplifier, now let us come to, so this is accelerator RTEC software of SCL. So here we configure our 3 actions, and the RTEC also we configure using this software. Okay. So I will not tell much about the settings because it differs from manufacturer to manufacturer. But what are the configuration we will show you. So first, let's say if we insert, so these protocols we can use. So we can send or receive our data in these kind of protocols. We can use C37118, DNP3, and Modbus and other protocols also. These protocols we can use to transfer data. Okay, so we, let's say we will select C37118, and then we have to select that this device will work as a server or client. So it will send the data or it will receive the data. So let's say we will select as servers, that it will send the data, and via what medium? Via Ethernet medium. So like this, if we insert, it will insert one device, and it will check the device what are the modules it has. So the current device, which is this, which I am showing, it has one CTPT module, one DI card, sorry, 2 DI cards and 1 DO card. So it will automatically come. Then which module you want to use, you have to go into, let's say we want to go to the CTPT module. So here we have given these settings. So this scaling factor 625.96 and this 781. So this scaling, this is for different current maybe I have done. So this scaling factor we have to give here. So now the output of this PMU will be same as what we are sending from the RTDS. Then we have to configure this device is sending to which device. So that is, so this device is sending to 2 devices actually. So one is to PDC. So this PMU is sending to PDC, and another one is, it is sending to a monitoring software. So that if you can see, yeah. So this is the monitoring software of the SCL. So in the top portion, it is what this PMU is sending, and at the bottom part, this is what the PDC is receiving. Okay, so this we can use for the comparison. So in the attacks cases, you will see that the PMU will are sending healthy data, and we will create different types of attacks, which you will see at the bottom level. Okay, so this is the yeah. So this is the software of the PDC. Okay, so the PDC we can send multiple PMUs. So we have this 3 PMU 50, 52 and 121 is there. These are hardware PMUs, and all these things we have to configure here. So here different PMUs. So PM 50, 52 and 21 hardware PMUs, and we have some software PMUs. Software PMUs we can send using the GTNet X2 card. And then this output is what this PDC is sending to this PC. So whatever this software it is showing, so it is showing in this PC. So that PDC is sending to this device. So there we have configured this output. Okay, and here also we can say the values. So 132 kV. So here also in the RTDS, okay. So here we are receiving around 132 kV volts. So same thing we can see at, and PMU is also sending 132 kV, and here same thing we are receiving here, and currents also in the range of 245, something like that. So this is the communication from RTDS, from GTO card to amplifier, then amplifier to PMU, and then PMU to PDC. Then I will just show you about the how to configure GTNet X2 cards. Uh, this is, let's say, the same 9-bus system. So here we have a module GTNet PMU8. So using this, we can configure 8 software PMUs. Okay, if you click here, it will first ask how many PMUs, maximum 8, you want to configure. So here I have selected 2, so these 2 will get enabled. Okay, so if you click any one of it, so here you have to select which phasor values you want to. So VA, VB, VC. So 12 phasors we have, values we have seen. In addition to this, we will also get frequency and rate of frequency, rate of changes frequency. So this is how we can configure, and we have also one more module, GTNet PMU24. So there we can configure 24 PMUs also. So this is the communication of PMU to PDC synchrophasor data, and also you can see the data in the Wireshark capture also. Uh, so if you filter, so you are seeing synchro. So if you filter only synchrophasor data, so here, as Professor Bhavesh has told you, so like this, we will get the hexadecimal value, and this we can encode it. And here also it shows. Okay, I will show you one sample file. So like this, we are seeing. So this is a test data I have collected that time. So like this, you will see phasor values also. So like this, we can see in the Wireshark also. So this we can take it as an input. We can save it as a PKF file, and we can take it to analyze in our, let's say, Python programming and all. We can take it as a. I will show you a real packet file. So like this, the phasor values comes when we enable the communication between PMU to PDC. Okay. So same thing we have also done it for DNP3 also. Aparna will tell you about the DNP3. Before that, if any questions. Same as this. Same, it you will get the same like this. It will, there will be no different. Yeah, we have to give input. Uh, Same, we have to give the 3-phase voltages and 3-phase currents as input, and it will generate the phasor values. Time stamping will be done using the GT sync card, and then it will send directly to the PDC using the Ethernet cable. And same thing you will see is, as you are seeing here, same thing you will see. So which module, for which no, this module itself is doing that. Yes. 9 substations. Yeah. Yes. 8 bus data we can take from here. Yes. Similarly, like this, we have 124 also. Yeah. Yes, yes, yes. Yes. Yes, yes. Thing is, what are the inputs to this PMU? Let's take the example of this simple system. What are the inputs of this? 3 voltages of this bus and 3 currents coming out of this line. And if we enable another 6 channels, for that we will give these as inputs, these 3 voltages, and the current coming out of this. So those, it will send different values for that, because that bus may have different voltages and different currents. So it all depends on what input we are giving here. So here we have enabled 6 channels. We can enable it as shall we move to the tier?
So, as already explained, like we can use multiple protocols. C37.118 for synchrophasor, it has already been explained. We explained while explaining the hardware that the PMUs we are using, these are actually Axions, like they have inbuilt RTEC properties. So we can use it for SCADA communication also, for example, using DNP3 or Modbus or IEC 104 based communication. So I'll be showing one of the example in which we are configuring these same PMUs inbuilt RTEC to enable the DNP3 based communication, how a master and slave communication based on DNP3 we are communicating. Maybe this can be used for SCADA communication or distribution automation communication for specifically RTU and control center, or RTU and SCADA based communication. So the same, this is RSCAD software, the where we can build 13 bus, let's say, distribution system model. We can modify it by using introducing DERs or anything based on our requirement. So let's say a 13 bus modified IEEE standard distribution system is modeled in RSCAD. Then this is the same, one of the sample network is shown, like from source to destination, how we will receive the data. In the similar way, we were receiving in PMU. Now our PMU will act as our RTU that will receive the data using this GTAO card. In this GTAO, again, the 6 channel, for example, 3 voltages of 3 currents or maybe feeder currents, we'll configure it as per our requirement. And the output scaling, the conversion factor, which was already explained. Now the voltage level will be different. For example, for distribution system, this voltage level will be, let's say, 4.16 kV. Earlier it was 230 kV. Now distribution system level, the voltage level will change, but the conversion factor would still remain the same for these devices. After that, we can also model, this is one of the hardware case, like one RTU via amplifier to, now destination is not PDC. Destination is, we can use the dedicated RTEC we shown you there. That can we can use it as one of our destination. That can also used as a data receiver, data concentrator, or a receiving device in our end. And for it, we can design our own HMI or own SCADA system. I'll explain to you like how we can design our own HMI in that. Okay, so that was one of the hardware route. For software PMUs, for example, software PMU we can model in RSCAD. Similarly, we can use like GTNet X2 card for various other protocols. For example, GTNet DNP is there. We can use it to directly configure, like these will be our slaves, and directly to our master. Our master will be that dedicated RTEC. So for using this, now DNP3 protocol is one of that protocol in which I think we have to map each and every measurement. Like 5 types of data points are there: analog input output, digital input output, binary counters, or these kind of data points. So you always have to map each point till the destination. Like data point number 1 would be our analog measurement and everything. Like you have to always tell that which data point belongs to which measurement, which type of measurement. So for that, here you can see a point map file list name as point map file. So while using this software DNP, you always have to make a .txt file in which you have to map all the measurement, and have to, like, otherwise RTDS won't understand which measurement to send to destination. So there are various binary input, double point input, analog input, binary input, and analog outputs. Like bi-directional communication, if you have to give like command back, so analog output and binary outputs are also there. Like after control command giving back to the IED, for example, trip something, or if something is going out of range, then reduce it. So all of these we can map it. So we have to specify this mapping while simulating and give it to the RTDS. If we are using GTNet X2 card, if we are using direct the hardware path, then we can directly configure using the RTEC. So now we have to use not only PMU and PDC, we have to make 2 RTEC configuration. Why? See, this is a very simple circuit. If we can understand sample network, master and client communication. Most of the DNP3 or say IEC 104 communication are based on master slave communication. Like master is your control center that would always ask for the data, and slave devices are your field devices. Let's say one RTU device. So master will always ask for pole of the measurement, polling, which is based on different types of pollings are there, like integrity polling or event based polling based on our substation requirement. So that is a master device. Master device is, in when we talk in terms of communication, becomes a client device, and slave or outstation device is RTU device, that would become our server. So this client and server network So basically the RTU device will get the power system input from RSCAD, and the slave device we will monitor, will develop our own HMI in that RTEC network. So this master and client communication based on DNP3. So we have to configure these two different profiles in RTEC. One considering the making one RTEC as a client, then configuring another RTEC device, making that as a slave. And then both of them we have to configure based on DNP3. Then several DNP3 based settings we have to do, like this will differ. This is SCL based RTEC, so settings would be different. For any other company, maybe the settings would be different. So we won't go in that detail, but protocol level detailing like IP address, port address, and everything, mapping of the points we have to do on the both RTEC devices to establish smooth DNP3 communication between them. Then we have to make tags also. There is one thing called tags processor. So all the data points are transferred using tags. We will analog, digital points, everything will make a server a shared mapping file. For example, whatever I showed in that GTNet mapping.txt file we made. So for using GTNet X2, we make a TXT file and map that. And while using the RTEC, we make this mapping as a DNP3 server shared map or tag processor inside it. This is the simple Wireshark capture. The network would be similar, like using the same network switch. We consider we have connected a PC. We'll monitor into the Wireshark, and these are the sample Wireshark capture in which we can observe like complete the protocol stack. Basically, three or pseudo 4 layer stack is the DNP3 protocol stack. So basically, our important power system related application will find into the application layer as a data point 1, 2, 3, 4. Okay, so that is why I already told you that in DNP3 or these legacy protocols, you have to always map the measurement. By looking at the Wireshark file, you won't know which measurement is what. So initial mapping is always required in such protocols. Now, if we use the hardware path and how to develop HMI, so in that RTEC, SCL RTEC, we have its own online interface in which we can observe the complete reports, alarms, or we can develop our own HMI and dump into it. So we can make the line diagram also, HMI diagram also, and the real-time trends, whatever data it is receiving in real time, we can make that also. For example, this is one of the snapshot in which three-phase voltages and three-phase currents, whatever we are receiving at the destination end, RTEC end, say SCADA end. So this is what we are observing. So in terms of cyber attack perspective, whenever we will perform attack, so data which we observe at the RTU or the field devices end, that would be healthy. But if it is being attacked, we can see it at the destination end, or at this HMI observation, we will see different types of attacks tomorrow, like how the voltage or currents can be manipulated. Any questions regarding this? So, yeah. Goose we are just going to do it in the next session. Yes, sir. That Axion devices, yes. 61850 also they are enabled, and Goose communication also we can do. And from these GTNet direct from RTDS also, like using this GTNet card, we can directly send Goose communication. We can do directly from there also. So now we'll move to Goose communication of relay.
So now we will see this Goose communication. So this is the similar setup. So now we will see that HIL that we have talked, like from previously from RTDS, we are giving it to from GTO card to amplifier, and from amplifier we were giving it to the PMU. Now instead of the PMU, we are giving it to the relay, and then relay, based on its logic, it is generating the trip signal, and that trip signal we are giving it back to the here using this GT-DI card. So this GT-FPI model is for that, and we are giving the output of it we are giving to this BRK breaker. So this is name of this breaker. So it will if any trip signal comes, it will open this breaker. So this we will see here. So this is the same quickset software that we saw yesterday. So here you can see we are getting the three phase voltages and currents, and currently it is enabled. And what we are doing is to enable the goose communication. We are so directly we can, if you want to give it back to the RTDS, we need to use that GTNet card. But now we to use the hardware device, we are sending this device, the data of this device using the goose communication to one of our Axion devices. Okay, one of the PMU. So we are sending it over here. This Axion device is not doing anything. It is just the digital output signals. It is redirecting. It is giving it back to the RTDS. So it is just a hop. Here we can design on our own logic, because in utility we cannot change the settings of the relay. So if we want to test anything of our own logic, another device we can, so this device we can use. It also has inbuilt RTX. We can design some logic here, and based on that we can send the goose. From here the output is digital out, and in the RTDS it is digital in. So let us create one fault. Here I will create one. So here here data is flowing now, and I am creating a fault here, same LG fault. So here the current has increased here, and the breakers has opened here. The current is 0 now. Here also, if you can see in the relay, it has tripped. And then we has the auto recloser also. So now if we refresh, the breaker has also closed again. So now again the data is flowing. And now we can see the goose messages, how it looks in Wireshark. So here we can enable this COM monitor. So all Ethernet traffic. So we are starting the traffic now. Okay, now let us create the fault. Okay, so we have created it as auto reclosed, and here also it has stripped. And let us close the Wireshark capture. Stop, and let us see what has come. So here if we filter with goose, so now these are the goose messages. So here we have to specifically focus on. So here it only records the events. If there is any change in the event, it records. So if you go down, so this is false now. So if we move to other packets, I think we closed the Vaisak too early. I will show you one sample packet. This false changes it to true whenever there is a trip signal, and then it again changes back to false whenever it is reclosed. So here you can see. So until now here it was from here up to, let's say here it was false. So here also just focus on this field, and here there is a event occurred where it has changed to true. So whenever it occurs, so if you come here, this st num previously it was 7 as 7. So whenever there is no change in event, this st num will be same, and this sq number it will increment by 1. And whenever there is a change in event, this st num changes increments by 1, and this sq num will reset to 0. And here you can see there is a change in the event. Now the value has changed to true. Now in the next also it is same true. So this st num is still 8, and the sq num is now increasing. So it will again be incrementing until the value was true, and then when we have auto reclosed, and then the value, this sq num will become 9. It has become 9, and then again sq num will reset to 0, and it will increment like this. So this is how the goose messages looks like. So this is how we do goose communication. So this is just we have uh, performed this, means enable this goose communication. Now in the next phase we will do attacks on this. So currently we have just established this goose communication. Any question? Sorry. हाँ okay. So if you see the field also, this field, I lost again. So if you click on this field, so previously it was 0 and now it has changed it to 1, this value. So this also is a one field we can check. So if you check the false condition, it will be 0, this value. One.